moving on to the properties of determinants. There are multiple ways in which people write determinants. So this is very common. Delta, det is obvious. Our preferred notation is this. First of all, the identity matrix has a determinant 1. Why is that? In 2 by 2, for instance, if you take the identity matrix, it's obvious. 1 times 1 minus 0 times 0, that is just 1. But even if you take the unit square and try to transform it using the identity matrix, it doesn't go anywhere. It stays the unit square, and that has an area 1. So I expand along the first row and first column, and that will evaluate to 1 in any dimension, not merely 2. Exchange 2 rows or 2 columns, the determinant changes sign. So that has some important implications in terms of so-called permutation matrices. Permutation basically means you are swapping a pair of rows or a pair of columns. The idea is that since the determinant changes sign, by odd number of permutations, you cannot get back to the original matrix. So you can take, say, first and second row, swap them once, you get a different matrix, swap them back again, then you get the original matrix. So that's 2 permutation. There's no way in which you can do 5 or 7 or 9 or 101 permutations, swappings, to get back to the original. It has to be an even number of exchanges. So that's interesting. And this is probably the kind of things that you might come across in discrete mathematics. And you can also say that permutations will have to be either odd or even, depending on whether the determinant is negative or positive. It actually specifies the determinants of all permutation matrices, because if it is odd, then it has to be -1. If it is even, it is 1, which is quite nice. So let's take a look at a couple of permutation matrices here. So permutation matrices are basically identity matrices with some swapping. Row 1 and row 2 swapped in R2 would be the first permutation matrix here. You just do that to the identity matrix, you get that. Similarly, for row 1 and row 2 being swapped in R3 by 3. I should have actually said 2 by 2, but for reasons that might become obvious later in life, in your linear algebra life, this is sufficient. Okay, so it's swapping R1 and R2, you get this matrix, and that as a determinant of -1. And if you have multiple swaps, 2 in this case, if you sit down and compute the determinant, this is going to be +1. The next one is interesting. If you scale one row or one column by a scalar number, then the determinant is multiplied by that number. So if you scale all elements of a matrix, the determinant is not multiplied by that number. It is multiplied by that number to the power of the number of rows or number of columns. Can you see why? It comes from the fact that the determinant behaves like a volume or an area. If you take a square, side 1 and 1, double both the sides, then you get an area of 4. If you double only one side, which is like doubling one row or one column, then the area doubles. That's what I've written down here as the explanation of point number 3. Then the next one is, if you split one row or column up, the determinant gets split into 2. This sounds a bit mysterious, so let me explain that here. Suppose I can write a determinant by splitting the first row into 2 for each element, 2 parts for each element. Then the whole determinant gets split into 2 by the same kind of splitting. Properties 3 and 4 sound vaguely similar to the conditions of linearity from first chapter. It's not an accident. Determinants are actually what they call multilinear functions. It is linear in each row or each column, and that's why you can see additivity being respected per row or per column, and homogeneity, multiplication, also being respected on a per column or per row basis. Another thing is one column or one row being all zeros immediately implies that the determinant is 0. Why? Well, you just expand on that row that is 0 or that column that is 0, because you're allowed to expand on any row or any column. So every one of the Laplace formula terms will have a 0 multiplying it, so the whole determinant is 0. Now, the next one sounds a bit weird. It says add a multiple of a row to another row, then the determinant stays unchanged. This actually comes from the notion that a matrix is like the coefficients of a set of linear equations, a system of linear equations, and equation manipulations are basically scaling one equation and adding it to another equation so that you can eliminate some variables or whatever. And that doesn't change the solution set of the equations. And that is kind of encoded in here. But this can actually be proven using the properties of determinants. I will leave that to you as an exercise. Oh, by the way, if you add a multiple of a row to another row, the determinant doesn't change. But if you add a multiple of a row to itself, then you're basically scaling that row. And then the property number 3, then the determinant actually does change. So you have to add a multiple of a row to a different row. So property number 7 comes from property number 5 and 6. So you are allowed to add or subtract rows from each other. So if you have 2 rows the same, you subtract one from the other, then one of the rows becomes just 0. And then you can expand on that row to get 0 determinant. So 2 columns or rows being the same will imply that the determinant is 0. What that means in the case of systems of linear equations would be that 2 equations, the coefficients are the same. So if you subtract one equation from another, everything disappears. So it's as good as having just one equation, not 2. And that has some implications on the solvability of the system of linear equations. More properties. A triangular matrix has the determinant as the product of the diagonal elements. So that is very easy to see. If you have this triangular matrix, you just expand it along the first row. So A times the determinant of this guy. And what's the determinant of that guy? Is just df minus 0. So A, df, A, df. That's the determinant. So the proof, if it is a lower triangular matrix, to expand on the first row. If it is an upper triangular matrix, expand it on the first column. If the determinant is 0, then the matrix is singular. If the determinant is non-zero, then it's non-singular, which means it's invertible. So next week we will see how that comes about. So there are some terms here that are unfamiliar to you right now, but next week onwards, that's going to be fine. Then the determinant of a product is the same as the product of the determinants. This actually implies that the determinant of the inverse of a matrix is the reciprocal of the determinant. Why? Because A inverse is I. That is what inverse means. Then you take the determinant, both sides. Right hand side is just 1. A and A inverse are reciprocals of each other. And this is again neat because determinant in some sense behaves like the size of the transformation. The size of the inverse operation is like the reciprocal of the size of the forward operation. The determinant of the transpose is the same as the determinant of the original matrix. To compute the determinant of a matrix, you go along the first row, for instance. And in that case, for the determinant of the transpose, you just go along the first column. In the transpose, the first column is the same as the first row of the original matrix. So every single term in the Laplace expansion is going to be the same. Now, I have one exercise here. I actually worked it out here. And there is a more detailed step-by-step derivation of this in the textbook. We can actually derive the determinant of a 2 by 2 matrix using the properties. What that means is that the determinant of a 2 by 2 matrix, as we defined it, will obey the properties. But at the same time, if you did not have any idea of what the determinant was, then you came and said, okay, these are the properties that I would like the determinant to satisfy, then there's only one computation for 2 by 2, and that's what it says. So the determinant being AD minus BC is not merely our definition. It is the only number that can satisfy the properties that we are looking for in a determinant. Something interesting mathematically. So we have come to the end of the first part of this course. There are 4 parts. The first one was about the numerical techniques that you might need to compute different things and also introducing the basics. We saw that even though we defined vectors as just column matrices, a bunch of numbers standing in a column or list of numbers really, they can appear as line segments with arrow. There is some sense of direction in the cosine similarity in natural language processing. Then we saw even the determinant has some profound geometrical meaning as well as algebraic meaning. Algebraic in a sense that when it comes to the solutions of a system of linear equations, the determinant of the matrix, if it is a square matrix, has a lot to say about that. And this duality, shuttling between the geometric view and the algebraic view, is something that you have to develop because that's how you would become good computer scientists, because in order to visualize things in higher dimensions that you cannot really do numerically, you have to have the intuition, the geometric view. That way you come up with some ideas for your algorithms, and then when you actually implement it, you go back to the algebraic view whereby you actually have to write down the equations and put it down as programs or prototypes. This shuttling between these two views, perspectives, is essential. So next week, we will start our second part, whereby we will start looking at a matrix and start seeing the equations that the matrix, along with the constants vector, can represent. And then we will ask ourselves, when can we solve them? Can we always solve them if we have enough equations? Or if we have more than enough equations or too few? What do you do in these cases? That will be the mainstay of the next part. And that is what we will call the algebraic view of linear algebra. And that will start next week.